Okay, hello everyone. My name is Fedi Botros. I'm a researcher at Meta Reality Labs, and today I'll be presenting work from our team titled StegoType, surface typing from Egocentric cameras. So hand tracking has gained popularity as low-friction mode of input in AR and VR, alleviating the need for controllers to enable human-computer interaction that mirrors how we interact with the real world. Yet still, natural text input remains a challenge. Existing VR solutions for hand-based text entry include raycast or poke-based mid-air keyboards. They primarily utilize only thumb and index fingers, which limits their effective throughput. In our work, we demonstrate that multi-finger touch typing on flat surfaces can be achieved on any consumer VR headset. We introduce a real-time system integrating imperfect, egocentric, markerless hand tracking with a downstream text decoding model running on a compute-constrained device. In previous work from our group, we showed that high-fidelity marker-based hand tracking contained rich information sufficient for a user-specific motion model to predict what key user intended to type, even if they accidentally hit a neighboring key. Here, for example, you see a fingertip trajectory in green where a user underreached for the O key and accidentally landed on the I key. Comparing against reference trajectories, the trajectory shape looks more similar to the O examples than the I examples, which can enable a model to predict the user's intent. Here we expand on this work in two principal ways. First, we demonstrate that a similar approach can be applied to lower fidelity markerless egocentric hand tracking, as can be found in many consumer VR devices today. And two, we show that with a sufficiently diverse training corpus and a sufficiently expressive model, this approach can generalize to users outside of our training corpus. We constructed an environment where users don a VR headset and sit in front of a virtual keyboard superimposed upon a real-world physical surface. The headset contains a stereo pair of downward-facing cameras, which have visibility of the user's hands. The two cameras are calibrated to enable egocentric computer vision hand tracking. Camera frames are sampled at 30 Hz and fed into UIST, which outputs a stream of hand pose features at the same frequency. These hand pose features are then fed into a downstream streaming transformer-based motion model, which maps hand motion directly onto typed text. Training this transformer model requires a training corpus. For this, we designed and built a data collection apparatus. Starting from our previous work, we initially had participants transcribe prompts on a paper keyboard while wearing a set of head-mounted cameras without any feedback along the way. Whether users physically touched the exact key location was irrelevant. We simply had them self-declare whether they felt like they typed the prompt correctly, which gave us hand motions paired with the text people believed they typed, or put another way, their intent. As we scale up this data collection, we analyzed participants' typos and categorized them into two main groups. Slop errors result from users over or under reaching for keys, leading to a neighboring key being hit. For these errors, we want our model to predict the key the user meant to hit. And second, we have compliance errors. These are everything else, leaving out a letter from the prompt or reading and then typing the wrong word. If the user makes a compliance error, we don't want to label it with the prompt because the prompt doesn't match what's in the user's head. Unfortunately, in this open loop data, we found that participants made compliance errors in over 40% of transcribed phrases. To address this, we switched to a closed-loop data collection where users received live feedback from a touchpad keyboard. We embedded two Stencil touchpad boards underneath a full-size paper keyboard and built a software decoder to show users live transcription progress. Now labeling with the keys a user physically touches solves for compliance issue, but inadvertently eliminates the slop errors we aim to include. To introduce slop errors, we then modified our decoder with an oracle based on the transcription prompt. During transcription, we know the next key that should be hit. We use this privileged information to bias the touchpad decoder so that the key is roughly twice its normal size. This means that if a user physically touches close to the key they were meant to hit, we label it with the key from the prompt instead of the key they touched. On the other hand, if a user makes a compliance error, the oracle doesn't know what to expect next, so we bias the backspace key until they return to an error-free prefix. With this, we recorded a data set of 268,000 transcriptions from 606 unique participants, who were able to type with whatever level of slop they found natural. Because this setup is interactive and users correct their mistakes, this also gave us realistic training data for backspace key presses as well. We use this data to train our model. Our input features consist of a temporal sequence of 3 vertices per fingertip, along with scalar hand confidences. The fingertips are measured relative to the keyboard, to the virtual keyboard coordinate frame, and then fed into an architecture based on the informer, a streaming transformer adopted from the field of automatic speech recognition. The informer allows us to reap the benefits of expressive self-attention-based models while also enabling efficient incremental execution that was pivotal to running on all of this on a compute-constrained headset. When typing, the motions of the left and right hands are coarsely symmetric across the keyboard. We take advantage of this and modify our informer into a Siamese architecture. The right hand features are mirrored over the keyboard midline and fed into the same trunk that processes the left hand features, with late fusion to make our final key press predictions. While this model can leverage a temporal window of hand motion to predict key press, it is not aware of the key presses of the keys it already predicted. Inferring an intended key from a finger trajectory works better if you know what key that trajectory started from. This can help compensate for subtle drift of the hands over time, for example. We modified our model to be aware of its previous predictions by adding decoder heads at select intermediate layers inside the model. These intermediate heads share weights with the final decoder head and are supervised in the same way, effectively allowing the model to see its previous predictions. We compared this label-dependent Siamese informer to the more basic informer variants, as well as simple temporal convolutional model. All these models leverage 12.5 seconds motion history, but the label-dependent Siamese informer clearly outperformed, achieving a character error rate of 7% on an eval dataset of users not represented in our training corpus. Furthermore, though the informer models have slightly more parameters than the TCN, the cost to process a new frame of data is an order of magnitude lower than the TCN due to the efficient incremental self-attention mechanism. We train our models using the CTC loss function, also adopted from the field of speech recognition, where annotating the exact timing of phoneme starts and ends is a difficult task. While we have ground truth alignments from the touchpad, there are many cases like this. Here it is very challenging to identify the exact frame where the pinky makes contact only by looking at the hand tracking. Supervising with CTC allows the model to make better predictions by learning to sometimes lag based on the data. Of course, for keyboards, latency is a negative. Physical keyboards typically have around 20 milliseconds of latency, but we found that our CTC trained models had learned to wait 210 milliseconds on average before emitting a key. To address this, we introduced a supplemental loss term that minimizes the KL divergence between the model output at time t and t+1 for all time steps. If the model previously spiked at time t, this term encourages the model to instead spike at t-1, effectively causing events to fire earlier in time. This term allowed us to trade model accuracy for emission lag, and we selected a model that achieved comparable emission lag to the latency of a physical keyboard. Now, there are still fundamental limitations to egocentric hand tracking accuracy due to image fidelity and self-occlusion. In typing poses, the fingertip are often self-included, which makes the pose estimation problem ambiguous and oftentimes quite hard. To allow our motion model to reason about occlusion and what the hand tracker doesn't know, we extracted latent features from within the UMATrack hand tracker and concatenated these as input into our motion model. We found that these latent features yielded improvements to both accuracy and emission lag, especially helping cases where self-occlusion was the strongest. We recruited 18 participants for a user study to compare StegoType in VR against traditional keyboard input on PC. In VR, users saw a virtual keyboard, their virtual hands, and a window with a typing test. We ported the same typing test to PC for the physical keyboard condition. Neither condition used a language model or autocorrection. In both modalities, users adapted over multiple blocks. For StegoType in particular, block 3 at 47 words per minute was especially faster than block 1 at 35 words per minute. Participants also had a wide range of performances using StegoType relative to using a physical keyboard. For example, participant number 7 achieved 67% of their physical keyboard typing speed using StegoType at an uncorrected rate of only 1.2%. While participant number 5 achieved 49% of their physical keyboard typing speed at an uncorrected error rate of 22%. We did observe some differences in accuracy between our offline evaluations and our online study, suggesting a domain gap between the two settings. We noticed, for example, that users frequently rested their hands, their fingers in our study, but this never happened in our offline data, where users reacted to feedback from the touchpad keyboard. We hope to address this gap in future work. So in summary, in our work we demonstrated that multi-finger touch typing on flat surfaces can be achieved on a consumer VR headset with low fidelity, markerless, egocentric hand tracking. We showed that with a sufficiently diverse data set and sufficiently expressive model, this method can generalize to users outside of our training corpus. And with that, I'll wrap things up and take any questions. Thank you.
Really amazing work. Yeah. So my question is, so it's been demonstrated in like brain-computer interface, speech prosthesis, is that when you have a natural language task, for example, typing or speech, it's much better that you start with the foundational models, with the natural language embeddings, and then you have some kind of convolution, whatever you want to do. But here you have a really lightweight e-former, so it's not a foundation model, rather it's actually a lightweight transformer. Like, I'm trying to get why you do this design choice instead of having a foundational models and then you have some kind of like motion, like embedding, like architectures, and then because like the good thing about natural language embedding is that, for example, happy is not going to be like another. It's going to be y at the end, right? And then the problem with natural language like models is that they are not able to get off that. If I want to like type random words, it's very hard to use this kind of foundational model embeddings. So, but the training set that you have is all natural language. So I'm wondering, like, if you want to leverage some kind of end-to-end like compression of the data, you might want to have some random characters rather than some natural language, which like you still get the natural language problems that like basically that like it's going to be a natural language rather like the user. Have you tried this? Like the user try to type something that doesn't exist in natural language and then see if the system still work? Yeah.
Yeah, good question. So yesterday in our demo, if you actually tried out, we had an autocorrection kind of integrated. We had a language model integrated to help make corrections. But we don't want to rely on that, because in the real world, we want users to be able to use this for passwords, for writing in different languages, for writing a lot of non-language text as well. So this is why we didn't run our study with a language model. But we can easily apply it, yeah.
But the data set you use is natural language data set, right?
It's both. So we did, users were doing both natural language and just random strings of text.
I see.
Yeah.
Thank you.
Yeah, I'll keep it quick then. Hello, Ishan from Google. I'm more curious on the interaction of typing on the surface. I've never used a Sensel keyboard or something where you have to sort of hover your hands above the surface. I know in traditional keyboard, you're allowed to ergonomically just rest it on there and then depress the key. How does it feel? Is this actually a good North Star to pursue? What are your thoughts around this?
Yeah, I mean, yeah, this is one of those things I can describe it, but it won't do it justice. You kind of have to try it. But in general, this is, I think users, like, it takes them probably like 1 to 2 minutes to really get used to it. But at the same time, this is one of the biggest like feedbacks we get is like, oh, I'm really used to rehoming using the F&J key, like using those nubs on the F&J key. So this is the one thing that people notice is missing right away. Because a lot of times when they're typing using this, if they look away or whatever really quick, sometimes they lose their position of their hand, and now they have to look down again to like move it again to the right spot. So this is the main concern. But if your hand is splanted and doesn't move, people can type very fast on this. Yeah. Thank you.
All right, thank you, Fadi.